Hello, welcome guys. Uh, Last time we discussed about the linear search and binary search in an array. Uh, this time we are going to take it forward and discuss about how to search in two-dimensional arrays. We will take two approaches again this time, the linear search first and then the binary search. So yeah, let's get started. So let's take an example of an array. For example, the array is a 2D array, by the way, looks like this. Let's take an even array where the even array means n. The even array means n into n. So 10, 20, 30, 40. Take a comma. uh, 50, 60, 70, 80, 90, 100, 110, 120, and 130, 140, 150, and 160. Alright, so we are taking an even array for this case. Now when we say we are going to use two approaches, let's start with the first approach, which is what we know as the linear search. The linear search has the time complexity of big O of n cases, which basically means that it will search the entire array, whether it is 1D, 2D, 3D, doesn't care what dimension the array consists of. So it will search the entire, traverse the entire array one by one till it finds its target. And like I said, the worst case scenario is big O of n, where either the target element is the very last element in the array, or the target element is not found at all in the array. So let's start with the linear approach. So let's see how the loop over here works. So big O of n, when I say about linear search, it is for one dimensional array, 1D. We will discuss why I'm specifying why it's for 1D. So let's pick a target for this array. Let's say I want to go for 110. So my target element is 110. Okay, so let's take a for loop. Uh, Before I start with the looping and how the loop works, let's discuss about rows and columns. When it comes to arrays, we can classify the entire structure into rows and columns. If you have heard about the grid system in maths and statistics and all, then we can see that there are rows, which are basically these, and there are columns, which are basically these. So the rows the rows determine the length of the array. Let's say there are four rows and there are four columns. So we can say it's an 4 by 4 2D array. Now when we say 4 by 4, the first 4 represents the rows and the second number represents the uh, column. So when we say we are going to traverse the array, the searching will happen from the very first element, from the first row and the first column. So um, in the simple array, we say indexing, right? So let's say there are 0, 1, 2, 0, 1, 2, 3. Uh, the indexing in a one dimensional array works like this. This is the first element, this is the second element, this is the third, and this is the fourth. And in terms of indexes, it's 0, 1, and 2 because the array starts from 0. So similarly, likewise, in two dimensional arrays, the same way indexing will work. So in the first row and first column, this is the very first element, so we can represent it as 0 comma 0. This will be 0 comma 1, 0 comma 1, this will be 0 comma 2, and this will be uh, 0 comma 3. The 0 here represents the first row, it's the row number, and the 0, 1, 2, and 3, the ones which keeps incrementing, are the elements of the column, because there are 4 elements in the column. So we are traversing the entire first row, column by column. So it will start from the first row and first column, where the first element is 0 comma 0. Then it will go for 0 comma 1, which is the second element in the first row. Then it will go for 0 comma 2, then 0 comma 3. Once the first row entire is traversed, it will move on to the second row, where the indexing will start from 1, 1 comma 1, 1 comma 2, 1 comma 3, and 1 comma 4, 1 comma 3, 1 comma 0, sorry, my fault, 1 comma 0, 1, 2, 3, 1 comma 3. So that's how the entire traverser takes place. Now finally, once we know about how the indexing works in the two-dimensional arrays, we can talk about the loops. Since there are two rows and since there are two dimensions, which is rows and columns, we will be taking two for loops, one that traverses the entire rows and one that traverses the entire columns. So let's see how that works. uh, Remember, we are talking about the linear search. So for int rows, we can start from 0. All right, so first row, we are traversing from the first row. Rows less than arr dot length, uh, row plus plus. All right, that's the first loop. Now the second loop, which is going to be for the columns. So for int calls equals 0, calls less than. Now here we can't take arr dot length, because the arr dot length is only going to work for the rows, which is 4 in this case. If we want to get the column count of each row, we have to take the column count for each row, because in this example it's a 4 by 4, means even, but every time it won't be even, right? Because there could be cases where the let's say, for example, this is an structure of the array 1 2 3, 1 comma 2, 0. So here in the first row there are 3 columns, in the second one there are 2, and then in the third there are 1. So we can't take a static number every time. So for that, we are going to take the number of column count from each row. So here row of 0, row of I, or here we are going to take the column count of each row, that is arr of row dot length, and calls plus plus. Now this will traverse the entire column one by one. So we are into second loop. Now here we can say that we have to traverse from the first row and first column, element by element. Now here we can match the target. So we can put a simple if case, that if the target element is equals to the element of row and that column, meaning arr of that row, particular row, and that particular column, we can say that the target is matched, right? So it's a simple if case. If the target matches, then we simply return the target, return the element index. It's up to us if we going if we want to return the index. In very specific cases, we can also return the that element itself, but that doesn't make sense because the target itself is the element. So why would we return the element itself? So we basically return the index. So in such cases we can return a string maybe of a row comma calls, literal string of row comma calls. um, in some cases we can make a new array of row comma calls containing the indexes of row comma calls and all. So now remember I said that for the linear search, the for one dimensional array, that time complexity will be big O of n. But now you can see that since there are two for loops, 1 and 2, it can't be big O of n because we are going for loop within a loop. For the worst case scenario, like I explained, it could be the very last element where the entire two-dimensional array needs to be searched. So in that case, we are going to traverse every loop and every loop within the loop to find that element. So in that case, the time complexity will be big O of n square. So basically, the general formula we can say is that the number of rows that are present in the two-dimensional array will be will be the power of the n over here. It is 2 because there are two rows, right? So let's say there are r number of rows in an array, then we can say that its time complexity will be big O of r. Basically, it's a very simple case that how many number of rows you have in the two-dimensional array, that many times there will be loop within a loop within that array. So it's not that difficult to understand. So I hope it's very easy to understand what concepts I'm teaching you as well. So that's the general formula that I gave you right now. But usually in data structures and interviews and all, the most they can go for is the three-dimensional array. And like I said, if it's three-dimensional array, then the time complexity will be big O of n cube, where there will be loop within a loop within a loop. We will talk about three-dimensional arrays later in the playlist. For now, let's get to the binary approach. So binary. Now remember from the last video that binary, when we talk about binary approach, the array needs to be sorted. Now here we can say that there are two types of sortings that we can apply over here. One is very strictly sorted, where I'll be giving you two examples and it will get very easy to grasp what I'm saying. I will take a 3 by 3. We can take n number of elements, but to make it easy I'm going for n is to n. So it's easy to visualize the array. So let's say 10, 11, 12, comma 13, 14, 15, comma 16, 17, 18. This is the first example that I gave you. Now as you can see, it's strictly sorted, meaning each element comes one after one. Means obviously there can be gaps between the elements. The range can be wide, but I just took it one after one. So it's strictly sorted. The manner is very strict over here, where each element taking place after the first in the row is sorted, and likewise in the column it's sorted as well. And overall the entire array, 2D array, is in a sequence. So we can say it's strictly sorted. Now this is the second approach. This is the second example that I will be giving you. 10, 20, 30, 80, 90, 100, 150, 160, 170. These are just random sequences. It's nothing related to something that I am going to explain. So here you can see that it's definitely not in a sequence. Means it is in a order, meaning it's in ascending order. But what I want to point out over here is that each row and each column is sorted in ascending order or descending order. We are talking about ascending. The same opposite conditions apply for the descending order. So let's talk about the ascending one. So each row in each column is is in ascending order: 10, 20, and 30, 80, 90, and 100, 150, 160, and 170. All right. So that too seems to be a strictly one, to be honest. Let me exactly take up the example that I wanted to use. All right, so to be honest, this is a strict one as well. The example that I want to use is a 10, 20, 30, 40, 15, 25, 35, 45, 28, 29, 37, and 49, and 33, 34, 38, and 50. Alright, so this is the example that I wanted to use. Here we can see that each row is sorted and each column is sorted, but we can also see that the last element of each row is smaller than the first element in the second row, means the row that comes after it. So here we can say that 15 is greater than the 10, 28 is greater than 15, 33 is greater than 28. All right, so same applies for the columns. 40 is greater than 10, the first element. 45 greater than 35, greater than 25. So everything is not that much strictly sorted. Here we can use a common condition. Now, of course, we can always use a linear search, because linear search does not require the array to be sorted in any order. We can always use the linear brute force approach, which is linear search over here. Let's say our target is 37. Target equals 37. Now, here we can see that when we search the array. Now let's talk about the binary approach. Now I'm going to explain how the binary approach in two-dimensional array works. So let's say our target element is 37. Now when we use the brute force approach over here, it's going to traverse from 10, 20, 30, 40, right? So here we can say, if you can notice a pattern, that this entire last column, which is 40, 45, 49, and 50, is greater than 37. You know that in binary approach, we know that we take the divide the array into half and half and half when we talked about the one-dimensional array. So we know that we also need to omit portions of the array and search from the portion that we know that the target is going to be from. So here we apply the same approach over here. So let's say that 40, 45, 49, 50, this entire column, we know that all the elements are greater than the 37th, which is the target over here. So we can say that we omit this entire row column. If we omit the entire column, it won't give us any harm or any error, because we know that the 37 is going to be less than that entire column. So we know that if we even omit it, then it's in fact saving us time, right? So let's say we omit the first column entirely in the first iteration. So now our entire array is now reduced to this one, this entire one. So it's a 3 by 4 matrix now. 4 by 3 matrix now. There are 4 rows and 3 columns only now. We entirely removed one column. So now let's move towards the third column. Now 30, 35, 37, and 38. Now we know that if we take this entire column into consideration, where 30 is the first element and 38, which is the last element. In binary approach, we need to give it ranges, start and end, if you remember. So the start over here is going to be 30 and the end is over here, end is going to be 38. So we know that in 38 our target is going to be there, right? So let's say we are going in the third column. So 37 does lie in this column, right? So we uh, now we know that third column is the one, but which row, right? So now we start, you know, so now we start to uh, keep going with the rows. Now that we figured out that which column is the one, we can start with the rows. So here we can say that 37 is greater than this entire first row. We remember that we omitted the 40th one, so entire that column. So 10, 20 and 30, we know that the entire first row is going to be less than the target, or target is greater than the first row. So we increment the row entirely. We don't need to even search in the first row because we know that the target is going to be greater than the entire row. So why even waste time in searching that first row? Why even waste time traversing that entire row? So we skip that row. So now our array is reduced to this one, 3 by 3. And remember, in side by side we are also omitting the columns, so it's a 3 by 3 now. I'm sorry it's getting a bit messy, but I hope you are still hooked on to the explanation. So it's a 3 by 3 now. So now we are going to traverse the second row where 15, 25 and 35. Now we again know that the 35 that the 37 is still greater than the entire second row, right? So we again do row plus plus. So we omit the second row. Now we are going to be in the third one where 28 to 37. We now same way as we applied the ranges where 15 to 35, 28 to 37. Now we again apply the ranges 28 to 37. Now we know that the target is going to be in this range. So we just reduced our range to this three. It's a 2 by 3 matrix in the end. So we know that we reduced it to the one column and we reduced it to one row. Now it's a simple 28 to 37, which is a linear binary search. So it will do its thing. So basically what I am trying to say to the condition where start and end applies to each row and each column, that when you start from columns, we start from the last column and start from the first row here, sorted one, remember. So if it's great, if the target element is great is lesser than the entire than the entire last column, then we know that it's going to lie in the range above after it. So it's out of bounds target. So it's out of bounds, we don't even need to check it. Now if it lies less than that last entire column, then we do column minus minus. So we move towards this one, we do the start to end. Similarly, likewise on the second side, we are doing with the rows ones, that if the target is greater than the ranges of the entire first row, then we don't even need to check that first row. So we do the row plus plus, row plus plus. So basically the loop runs with this principle that the column keeps decreasing and the row keeps increasing. So from the extreme end of the last element of the first row, means the last element of the first row, it will start its traversal. If it's lesser than the ones, then we know we have to come back a bit. It will keep minimizing the range of the array. That's how it keeps finding that array. We are not exactly going to say that it's doing a binary search, but it's doing a binary search in that row and that column. Whenever we reduce it and increment the rows and columns, it does it's doing its things. So let's implement all of this in a code wise manner, so it gives you more idea. So we know that it's going to return an array of indices. So we can say that int something, the name of the function, where we take the target element and the entire array. All right. Now inside the loop, we can say that we have to initialize the rows and columns. So we initialize the row as 0 and initialize the column equals uh, array of that row dot length, because like I said. All right, now what happens afterwards? We put a loop. Sorry, now we put a while loop. While start is greater than end, over here we can say that while row is less than matrix dot length, means the array dot length, and remember we are going to put two checks over here. This is a pseudo code, by the way, so the and exactly doesn't work at all if you start writing that. So row is greater less than array dot length, and calls is greater than or equals to 0, because we are starting from the last column. Now we put our checks over here, that if the array of that row means the element of that row and that column um of that row and that row matches the target, then we simply return that row comma column. Otherwise, now this is the base condition, that if it matches the target, then we simply return those indexes. Now so if otherwise, we can say that if the array that element is less than the target, then what we need to do, like I said, if it's less than the target, we reduce the number of columns, right? So we say we reduce the number of columns, rows, we increment the number of rows, because if it's less than that, see this element, if it's less than the target, means it's in the wrong row, we need to go further down. So for going further down, we have to say we have to go row plus plus. Otherwise, means if that element is greater than the target, meaning uh, that element else, means else if, we can use with else if. So you can see what condition I'm going to write, that element is greater than the target, means we are ahead of the target element. So we simply need to cut down the number of columns. So see minus minus, you need to go from here to here to here. So we are simply cutting down the columns over here. It's a simple if else case, nothing more, nothing fancy. And these ones will simply increment and decrement the rows and columns count. The matching will only happen over here. If it doesn't, then we can simply come out of the while loop, because the while loop will get violated once the row or column reaches to the 0. So it will exit that loop, and we can say return minus 1 comma minus 1, because the element is not in that that index. So we can simply return minus 1 minus 1. So this is the entire structure, entire logic of how the binary search in two-dimensional arrays works. I hope it gives you some clarity as to how the traversal takes place and how the omission takes place inside the binary search. And by the way, if you are wondering that what's the time complexity, then it's say log n big. So that's what it is. Thank you. We will be actually starting with some questions from the next video onwards. I hope you keep sharing my videos, keep subscribing, because I will always appreciate some inputs of suggestions and all. So yeah, many more to come. Many much explanations to come forth. Thank you.